Chemistry of aromatic compounds. In this chapter, we will discuss the structure of benzene based on resonance theory or the delocalization of pi electrons in benzene. We will learn how delocalization of electrons in some cyclic structures could lead to aromatic stability. We will learn to predict if a cyclic structure would be aromatic or non-aromatic based on Hückel rule. We will learn how aromatic stability of benzene influences its reactivity in electrophilic aromatic substitution reactions. We will learn how a substituent in benzene ring influences the rate of substitution and regioselectivity of a second substituent in electrophilic aromatic substitution reactions. We will learn to synthesize multi-substituted benzenes based on the ortho or para-directing influence of substituents. Structure of arenes. Structure of benzene. Arenes are aromatic hydrocarbons exemplified by its first member benzene. Benzene is currently represented by the structure A or B, first put forward by Hückel in 1865. It is a structure with 6 sp2 carbons in a ring with alternate single and double bonds. Note that the p orbitals in benzene can overlap in two ways. It has been found that neither A nor B correctly represent the true structure of benzene. Evidence to this end has been presented. Example, X-ray diffraction showed that benzene is a regular hexagon and all the CC bond lengths are equal and is 1.40 angstrom units. This is in between the length of a single bond and a double bond. All the CCC bond angles are also equal and is 120 degrees. From this, it is clear that in benzene there are no alternate single and double bonds. If there were alternate single and double bonds, all bond lengths would not be equal. The question is, if the Hückel structure A or B is not the true structure of benzene, then why do we continue to represent its structure as in A or B? Also, do we know the true structure of benzene? We will answer these questions in the next section. Resonance or delocalization of pi electrons in benzene. The resonance theory says that although benzene cannot be adequately represented by either Hückel structure A or B, the two together can be used to adequately represent the structure of benzene. In the resonance theory, the structures A and B are referred to as resonance structures or contributing structures, and the actual structure of benzene is said to be a hybrid of the two structures called resonance hybrid. A double-headed arrow connects A and B. The resonance structures A and B are hypothetical structures that do not have any reality. Since we are unable to represent the correct structure of benzene by a single Lewis structure, we use the two equally valid Lewis structures and say that the actual structure is a hybrid of the two. It is clear that there are no alternate single and double bonds in benzene. This is to say that the pi electrons are not fixed or localized between any two carbons. In other words, the pi electrons are delocalized in benzene. The delocalization of the pi electrons can be represented by putting a circle inside a hexagon. To track the pi electrons in benzene, it is still represented by the Hückel structures A or B. Delocalization of pi electrons makes benzene very stable. Benzene is an unusually stable compound in spite of having 3 conjugated double bonds or 3 degrees of unsaturation. The heat of hydrogenation data shows that benzene is stable by an impressive 36 kilocalories per mole. Based on the heat of hydrogenation of cyclohexene for one double bond, benzene is expected to have a heat of hydrogenation of 85.8 kilocalories per mole for 3 double bonds. However, its actual heat of hydrogenation is only 49.8 kilocalories per mole. The excess energy, that is 36 kilocalories per mole, by which benzene is stable over its calculated heat of hydrogenation, is known as its resonance energy. Aromaticity and Hückel rule. Compounds like benzene, in which the delocalization of electrons in a cyclic ring structure leads to extreme stability, are known as aromatic compounds. Hückel rules lays down the conditions for a molecule to exhibit aromatic stability. Rule 1. For a molecule to be aromatic, it must have a planar and cyclic structure, and all atoms in the ring structure must be able to support pi electrons or p orbitals. For a molecule to be aromatic, it must have 4n plus 2 electrons, where n has a whole number values of 0, 1, 2, 3, etc. Benzene is aromatic since it has contiguous pi electron bearing atoms and it has 6 pi electrons in a cyclic system, 4n plus 2 electrons where n is equal to 1. Naphthalene is also aromatic since it has contiguous pi electron bearing atoms and it has 10 pi electrons in a cyclic system, 4n plus 2 electrons where n is equal to 2. Heterocyclic aromatic compounds. Heterocyclic compounds, pyrrole, furan, and thiophene, are also aromatic since they obey the Hückel rules. The heteroatoms nitrogen, oxygen, and sulfur in these molecules are in sp2 hybridization state with one pair of electrons in p orbital. Along with pi electrons, they have 6 electrons, 4n plus 2 electrons where n is equal to 1. Note that the electrons in the sp2 orbital is not to be counted for applying Hückel rule. Aromaticity influences chemical reactivity. Imidazole is also aromatic. It is a much stronger base than pyrrole, as it protonates the nitrogen atom of imidazole containing the sp2 electrons. This makes imidazole retain its aromatic stability even after protonation. On the other hand, if pyrrole donates a pair of electrons, it loses its aromaticity. Therefore, pyrrole is a poor base. Aromaticity influences chemical reactivity. Many organic reactions are influenced by the aromatic stability of the product formed. Example, cycloheptatrienyl bromide readily dissolves in water to exist in an ionic form as cycloheptatrienyl cation and bromide ion. This is due to the aromatic stability of the cycloheptatrienyl cation, also known as tropylium ion. Normally, alkyl halides where the C halogen bond is covalent or insoluble in water. Potassium metal readily dissolves in cyclooctatetraene by donating 2 electrons to the cyclooctatetraene system. The anion of this compound exists as a dianion containing 10 electrons in an 8-carbon planar ring. This dianion obeys the Hückel rules and has aromatic stability. Normally, potassium will not dissolve in a hydrocarbon solvent. The influence of aromaticity on the reactivity of benzene. Ethylene readily undergoes electrophilic addition reaction when treated with bromine to give dibromoethane. Under similar conditions, benzene does not undergo electrophilic addition reaction. However, when treated with bromine in the presence of ferric bromide, benzene undergoes electrophilic substitution reaction to give bromobenzene, which results in the preservation of aromatic stability.